Hello everyone. Um, this is Priscilla Chamenyi here coming to you once again with this series of video lectures on unsupervised learning algorithms and the algorithms under this kind of learning. My name is Priscilla Chamenyi. I am a junior data scientist for global communities in the Laboratory of Data Science at Purdue University, Fort Worth. In the last video, the algorithm we looked at was DB-scan, which was a clustering algorithm. In this video, however, we're going to be talking about probabilistic clustering methods. So we're going to be looking at probabilistic models. And what are these models? They are statistical models that use probabilities and statistical data to make predictions and understand complex relationships in data. They help solve soft clustering problems. Some of the applications are in NLPs, natural language processing. In these kinds of problems or in these kinds of settings, they are used to analyze and understand relationships between words and phrases in text. In machine learning, they are used to estimate probabilities and model complex interactions between variables. They can be computationally expensive and they require careful modeling and tuning to produce accurate results. Now, an example of a probabilistic model is Gaussian mixture models. Note, it is still under unsupervised learning algorithm. Now, this probabilistic generative model assumes that the data points in a data set come from a mixture of multiple Gaussian distributions. And it is primarily used to determine which Gaussian or normal probability distribution a given data point belongs to. If the mean or variance are known, then we can determine the distribution a data point belongs to. In GMMs, the mean and the variance are not known, and we estimate these parameters using the expectation maximization algorithm. In the next series, in the next video, we will be looking at expectation maximization algorithm in depth. But for now, we're going to talk about how it is used in GMMs. So back to GMMs. So when the mean and variance are estimated, then for each data point in a data set, the probability of that data point belonging to a Gaussian distribution would be calculated. Now, because it is soft clustering, if the probability is large, then the data point is more likely to belong to that Gaussian distribution. And if it is small, it is less likely to belong to it. Now we're going to look at how the algorithm works. So, as I already mentioned, the mean and the variance parameters are estimated using the EM algorithm. The EM algorithm is a two-step process, and it iteratively estimates the parameters of the model and improves the fit to the data. So the first step is the expectation step, that's the E step. And in the first step, the responsibility of each cluster for each data point is calculated. Then, using the current estimate of the parameters of the Gaussian distribution, a probability is computed for each data point to belong to each cluster. Now, this gives the responsibilities of each cluster for each data point. In the second step, that is the maximization step, the parameters of the Gaussian distributions are updated based on the responsibilities calculated in the first step. The mean and the covariance metrics for each distribution are estimated using the weighted sum of the data points assigned to each clusters. The two steps are going to be repeated until convergence or a maximum number of iterations is reached. The final result of the EM algorithm is an estimate of the parameters of the Gaussian distribution that best fits the data. Here are some advantages of the Gaussian mixture model. It is flexible and can model complex distributions. It allows for each data point to be assigned to multiple clusters with different probabilities. That is soft clustering. And it can be used to select the optimal number of clusters. On the downside, the estimation of the parameters of the Gaussian distribution can be slow. It is also sensitive to initialization, and then it assumes that data points come from a mixture of Gaussian distributions. Now here is an example code in R using the iris dataset. This dataset consists of 150 iris flower as data points. Our four numerical features are sepal length, sepal width, petal length, and petal width, all in centimeters. And our only categorical attribute is the species of the iris flower. So in this R code, again, we are going to fit the Gaussian mixture model to the data set, and then we are going to plot the outcome. Now, the output of applying the GMM algorithm on the iris data set gives us two clustering, and as you can see on your right hand side, on your left hand side, on the left hand side of the screen, we see the clustering table that is giving us the components of each cluster. The first cluster has 50 data points and the second has 100 data points. We can see the visualization on the right side of the window. Then the output also gives us the log likelihood, and it gives us the log likelihood and the BIC of the model. We have a log likelihood of -215.726, which measures the probability of the data given the model, and we have a BIC value of -561.73. BIC values are used for model selection, and lower values indicate a better model. Generally, the log likelihood and the BIC would be used to inform model selection. So this is the output gotten from using GMM. So this brings us to the end of today's video. In the next video, we are going to be looking in depth into the EM algorithm. Stay tuned. This video was brought to you by Laboratory of Data Science and the Indiana Data Mine Grant, and it is supervised by Professor Alessandro Selvitella. Until we meet again, bye.